Okay, so what I'm going to do is I'm going to present what a batteryless tamper-resistant enclosure actually is. I'll show you the signal processing path that is needed to get the sensor data out, the actual measurement circuits and some of the results we have done, and then some security chip data and some conclusions that remain and some further work that will need to be done. So what is this tamper-resistant enclosure? For example, in an ATM, an automatic teller machine, you will need some kind of communication to the outside. Usually this is done by a VPN mechanism, but you want to protect your secret communication codes, the keys for the communication, from tampering, from anyone getting access to them and doing their own special, very illegal transactions. So you will have to somehow protect your circuit. This is the inside. Now, on the around it, we are putting a second casing consisting of a shield, two layers of interdigitated and crisscrossing wires, and around it, potting resin to protect and stabilize the whole package. Before, what was done in these cases was to have an internal battery that would power the whole thing all the time, even if the mains power would go out, and the whole array would be sampled resistively. Now, having batteries inside things has a lot of disadvantages, especially when it comes to recycling and things like this. But when the battery is defect, then the whole thing won't work anymore. And if you have a long enough power outage, the technicians will have to come and replace the whole thing. And there's a period of vulnerability in there. So having no battery obviously would be a big improvement. So what we decided to do is to use the capacitances inside this arrangement, not the resistances, and to use the capacitances as not only as a sensor for intrusion, as you would usually expect, but also as a path, so intrusions can be detected even if power is off. Okay, so the sensor elements, they are those crossings of the horizontal and vertical layers, horizontal and vertical wires on the different layers, which of course gives you a lot of crossover capacitance. And we are also quite interested in getting the capacitances here in those free areas, because they represent some kind of an area of weakness where you can drill a very tiny hole. The pitch here is 0.2 millimeters, a very small hole, and even reach the inside of the circuit without being detected. Now, using the fringe fields of these capacitors to detect those intrusions, we can even cover those areas between the wires. Now, the signal processing path of this part starts with the envelope. We are doing a capacitance measurement. We are also doing a traditional resistive measurement so that we can compare results. The sensor data, after some signal processing, is either used to raise an immediate alarm when the system is powered. That's pretty simple. We are doing, or the intent is to do something like one measurement over the whole array of 1 millisecond, or on power up, the sensor data is sent to a key generation unit, which extract from the sensor data the path information, turns this into an internal cipher key to decrypt the firmware and the necessary communication ciphers. If there is any intrusion in this capacitive sensor, then all copies of internal key data are zeroed when the device is operating. When the device is not operating, what will happen if there is some intrusion, intrusion happening, is that the path data will be disturbed so much that the internal key cannot be recovered anymore. So on startup, the firmware cannot be decrypted, the communication key cannot be decrypted, and the whole thing will not work anymore. But the secret is then lost. And the attacker can now open the package and he won't find anything that will be of use. This heartbeat signal here, of course, would be one bit that a fast attacker might be able to attack. So this is a PWM signal that is where the on time is generated by a random number generator at startup, so no one knows what exact time this signal must be high. And an attacker cannot measure it because the cycle time of this heartbeat is longer than the measurement time of the whole apparatus. So before the measurement of the attacker is finished, the measurement of the defender has already zeroized everything. So in more detail, what are we doing to extract the capacitance information from this array? So what we have is an array of 16 wires in horizontal direction, 16 wires in parallel dimension. So we have a total of 256 capacitances, which would have to be measured. As a matter of fact, we are only measuring half of these capacitances by measuring just capacitance differences between adjacent tracks. This has two big advantages. We can get rid of a lot of common mode signals, and we can also get rid of information that is not really relevant for extracting the POF data. The PUF data is almost pure due to this step. So what do we have? We have a driver circuit, which is exciting this array. We have an integrator, that's a switch capacitor integrator, which is amplifying the charge that is introduced into this array. Then we have a second order sigma delta modulator and a bank of sync filters, which are then delivering the final results. These results go into a digital signal processing unit, which is doing all the tamper detection. The SRAM here is, of course, of a type that can be cleared within a single cycle. And the data from here during operation is usually compared against the data obtained during a measurement cycle. If everything is okay, the heartbeat generator will go on generating its signal, otherwise it will be stopped immediately. This will result within a millisecond in a reset of the whole system. The capacitance measurement itself is pretty basic. Its core is a CDS amplifier, which we are using as a capacitive readout. So we are introducing the charges here. We're doing the necessary offset correction, of course, and get the amplifier. This internal capacitance here is variable in this instance because at the outset of this project, we didn't actually know what the actual capacitance would be because this is a tripartite operation. one group was responsible for building the capacitance array itself. There was quite a lot of novel film chemistry necessary to build those films. And beside our circuit group, there was a cryptography group which was doing the actual cryptography and puff evaluation. So we had to do quite a bit of variation in here. Now, on top of this, we built this as a difference signal, not a differential signal. That's going to be the next version, but as a differential signal. So we are taking the signal of a pair of receive lines, the horizontal ones, put them into these amplifiers in the first cycle, and then we exchange those two electrode connections and apply a drive voltage which is negative going, and then we get the same difference but inverted. This way we can eliminate quite a few common mode scenarios between those two amplifiers and get a nice big output signal. Okay, so this is one of the results we got by measuring discrete capacitances. It's pretty difficult to get capacitances off the shelf which have a difference which is defined to a precision of something like 1 femtofarad. So we bought a whole batch of them, measured them with a very accurate measurement instrument used in our semiconductor fab, and then measured it with our chip. And you can see, as a matter of fact, these arrow bars here, they should be arrow rectangles because we are already here in the error range of this instrument, which is plus minus 1 femtofarad. So these should be error pairs. As a matter of fact, we are not too worried about the fact that we have, for two different setup capacitor differences, one of the same difference which we are measuring. It's still within the precision of measurement. The main limiting, or the main limit we have for this circuit is temperature and supply voltage limitation. That is, those rejection ratios for them are not quite enough for good operation as a puff. It gives us something like 60 bits of cryptographic value, and we can't go, or we can go better with the next chip we are going to build. So this is the chip itself. It measures about 23 square millimeters, uses 400 milliwatts of power. Currently we have to run it slower than expected, 1 millisecond by a factor of 20, mainly due to the fact that the parasitic capacitances to the shields and the resistances of the wires themselves are much higher than we anticipated, so we have to run slowly. And this also degrades the performance of this chip. Still, we are getting a resolution of better than 2.2 femtofarad in the highest amplification mode, and the maximum input capacitance we have is about plus minus 2 picofarads. In common mode, we are getting a maximum of 80 picofarad, and there's a lot of headspace that we found. Now, here you see a picture of a very unsuccessful attack. This is a standardized attack in security documents using a drill with a diameter of 0.3 millimeters. So just to give you an impression how small the whole thing is. Okay. So as a conclusion, we've seen that we can realize this kind of a tamper-proof package with this approach. It will work in power down and power up mode using two different principles. for protection. The differential CDS sensing scheme is simple and effective and will be used for further operations. In the next generation, we intend to achieve both faster operation and better resolution, given us enough bits. Thank you for your attention. This is the engineering view of such a package. Engineering because we put the chip on the outside instead of the inside, so we can measure things. Thank you very much.